Countable and uncountable sets. In the world of mathematics, we often have sets of objects. The number of elements in the set can either be countable or uncountable in the case of some infinite sets. Let us look at the cardinality of a set. If we have a set of n elements, then the cardinality of the set is n. See here we have a set A which has 5 elements. Therefore the cardinality of this set would be 5. A finite set is always countable, but an infinite set can either be countable or uncountable. For example, in the case of the set of natural numbers, there are infinite numbers. Then that means the cardinality of n would be infinite. However, just because it's infinite doesn't mean that it's not countable. A set is said to be countable if it has the same cardinality as the set of natural numbers, even though the cardinality of the set of natural numbers is infinite. For example, let us create a set of even natural numbers n dash, which are equal to 2, 4, 6, 8, and so on. Now we can create a bijective mapping between n to n dash such that for x in n, the corresponding output in n dash should be 2x. And therefore this would cover every single element in n dash without leaving anything out, and therefore the cardinality of n dash is equal to cardinality n. Basically, we have to show that the elements of the set can put in such a order so that no element will either be repeated or no element will ever be missed out. Now, the set of natural numbers, the set of rational numbers, and the set of integers are all countable sets. Now, because we can create a bijective mapping from natural numbers n to q and n to z, we can say they're countable. I will show you now. See, n is from 1 to 2, 3, and so on. And now the integers 0, we can map it such that 1 is to 0, 2 is to 1, 3 is to minus 1, 4 is to 2, and 5 is to minus 2, and so on, such that for x and z, the corresponding output would be 2x or 2x plus 1. It will be 2x if x is greater than 0, and 2x plus 1 if x less than 0. And similarly, let us do it for the rational numbers, such that in q, it would be 1 mapped to 0, 1 mapped to 1 by 1, 3 mapped to 1 minus 1 by 1, and now we have exhausted all the possible combinations of 1. We take combinations of 1 and 2. So 4 mapped to 2, 2 by 1, and 5 mapped by 1 by 2, and so on. Therefore, all the elements are covered, and therefore the cardinality of q is equal to cardinality of n, and similarly cardinality of z is cardinality of n, and then there we can say that the set of natural numbers, the set of integers, and the set of rational numbers are all countable sets. However, the set of real numbers is an uncountable set. This is because we cannot prove a bijective mapping between R and N. This can be shown by using Cantor's diagonal method. Let us take a complete list of real numbers mapped to the set of natural numbers written in decimal form between 0 and 1. Therefore, this is the 0, 1 subset of the real numbers. Now, we take the diagonal elements of this infinite mapping 3, 2, 9, 5, and so on, and we make a new number out of this, and such that the first element of this would not be 3, the second element would not be 2, the second element would not 9, and so on. And we realize that we're creating a completely new number which does not exist in an infinite mapping, and therefore if we add this to the subset of R 0, 1, the cardinality of it would increase by 1, and therefore the mod R is not equal to mod n, but mod R is greater than mod n, and therefore we cannot create a bijecting mapping, and therefore the set of real numbers from 0, 1 uh, is not countable, and therefore this can be extended to the entire set of real numbers. Let S be a set. We can say S is countable if there exists an injective function f from S to the set of natural numbers, okay, and either S is empty or there exists a surjective function g from the set of natural numbers to S, and either S is finite or there exists a bijection h from the set of natural numbers to S. Now let us take two sets S and T. If the function f from S to T is injective, then T is countable and S is countable. And similarly, if the function g from S to T is surjective, then S is countable and T is countable. Simon Stevin, sometimes called Stevinus, was a Flemish mathematician, physicist, and military engineer. He was active in a great many areas of science and engineering, both theoretical and practical. He also translated various mathematical terms into Dutch, making it one of the few European languages in the word for mathematics, wiskunde, vis and kunde, that is, the knowledge of what is certain, was not a loanword from Greek, but a calque via Latin. Now we are going to discuss about some of his contributions to mathematics. Simon Stevin's most radical mathematical invention was his elegant way of representing decimal fractions and using them to carry out elementary calculations. His essay on the subject contains a description of decimal fractions, their application addition, subtraction, multiplication, division, and even briefly root extraction. Stevin writes in the same spirit of the practical applications of decimal fractions for dividing money and measurements of length, area, and volume, etc. Now, for example, let us take one of his notations, that is the decimal notation, 3172 53 and 94. Okay, this means 3 primes, 7 seconds, 5 thirds, and 9 fourths, and this can be continued infinitely. It can be seen from the definition that numbers are 3 by 10, 7 by 100, 5 by 1000, and 9 by 10 power 4, and that this number would be 3759 by 10,000. Likewise, 8, 0, 9, 1, 3, 2, and 7, 3 has a value 8, 9 by 10, 3 by 100, and 7 by 1000, making this number 8937 by 1000, and so on for other numbers. Also, you should realize that in these numbers we use no fractions, and then the number under each sign except 0 never exceeds 9. That is, we cannot write 7, 1 and 12, 2. However, we would write it as 8, 1, 8, 1 and 2, 2. Now we're going to start with exponential notation. The exponential notation, introduced by Bombelli in 1572, was taken over by Stevin with slight modifications, dispensed with the necessity of knowing all the signs and names. A single example will make it clear how greatly symbolic algebra was being improved by this innovation. From today, we use this algebra such as 5x power 4 plus 3x cubed plus 7x squared plus 2x plus 3. In this way, we represent a polynomial equation. However, it was written by Stevin as 5, 4 plus 3, 3 plus 7, 2 plus 2, 1 plus 3. This improvement will be appreciated even better when we add that the cosec signs, how it was represented in cosec signs, was 5 plus 3, were using this equation, reading from left to right, were pronounced respectively zenses de senses, cubus, zenses, and cosa, followed by such terms as sorsid solidus, sensi cubus, and visoridus solidus for the higher powers. This fatal influence which a traditional terminology and notation can exert may be realized more clearly when we consider that the mathematicians had tortured themselves for more than a century with the cosec names and signs before it occurred to anyone that one might equally well say first, second, and third quantity instead of these primus, secundus, and tertius. Now we discuss about interest, simple and compound, and profitable and unprofitable. Interest tables for the solution of problems of compound interest had been in use long before Stevin's time. However, the owners of such tables considered them as secret tools of their trade and refused their publication. Stevin was the first to do away with the secrecy altogether. He wrote an exhaustive textbook on the whole doctrine of interest and annexed to all the tables necessary for the solution of the problem proposed in it. This book contains a theory of simple as well as compound interest, both of which may be profitable or unprofitable. This means that in both cases, interest can be added to or subtracted from the principal. Now we discuss the roots of an equation contribution by Stevin. Stevin wrote his arithmetic in 1594. The work brought to the Western world for the first time a general solution of the quadratic equation, originally documented nearly a millennium previously by Brahmagupta in India. Stevin proved the intermediate value theorem for polynomials. Stevin uses a divide and conquer procedure, subdividing the interval into 10 equal parts, and uses this to prove this. In mathematical analysis, the intermediate value theorem states that if a continuous function from say a to b with interval a to b as domain takes values f of a and f of b at the ends, then it also takes any value between f of a and f of b at some point within the interval. Now we discuss Stevin's contribution in equilibrium of forces in trigonometry. Stevin was the first to show how to model regular and semi-regular polyhedra by delineating their frames in a plane. He also distinguished stable from unstable equilibria. He derived the condition for the balance of forces on inclined planes using a diagram with a red containing evenly spaced rounded masses rested on a plane of a triangular prism. He concluded that the weights required were proportional to the lengths of the sides on which they rested, assuming that the third side was horizontal and that the effect of the weight was reduced in a similar manner. It's implicit that the reduction factor is the height of the triangle divided by the side, the sine of the angle of the side with respect to the horizontal. Stevin also made contribution to trigonometry. This proof where the ret is placed on this triangle is known as the epitaph of Stevinus. Although Stevinus' conclusion is correct, his proof had certain logical defects as pointed out by Dichter-Huys. With theories so groundbreaking and an attitude so bold, it's not a surprise that Stevin was considered as a renowned scientific figure of his day.
So now we're going to discuss central limit theorem. Central limit theorem, as per in mathematical terms, and I'm literally just reading off text right here, is a statistical theory that states that given a sufficiently large sample size from a population that has a finite level of variance, the mean of all the samples from the same population will be approximately equal to the mean of the population. Now, that was in very abstract terms, so I'm going to explain the same concept with the help of an example. So, for the example, let's take the heights of all the human beings on planet Earth and let's map those heights based on the number of people who have the same number of heights. For our convenience, let's say that humans can only be either 120 centimeters tall, or 130 centimeters tall, or 140 centimeters tall, and so on till 160 centimeters tall. So, if we say draw a graph based on how many people have corresponding heights, say not a lot of people are 120 centimeter tall, a large number of people are 130 centimeter tall, a lot of people are 140 centimeter tall, an even larger number are 150 centimeter tall, but a small number are 160 centimeter tall. So from this set of values, or from this data that we have, let's make sample sizes of, for now, small sizes. So we have a sample set, of a small size, say 4. Say the sample set has 120 in it, it has 130, say another 130, and say maybe a 160. So if we take the sample set and we try to find the average of the values in the sample set, we'd see that this would be 250, 380, 480 and 540. 540 by 4, which would come to approximately 135. So 135 is the average of all the heights in the sample set. Now say we take a large number of such sample sets of similar size 4 and find the averages. Say the average could come out to 128.25, another 135, etc. Now, if say we take this data of averages of heights and plot it on a graph, that is, plot the distribution of these heights on a graph, we start to notice a sort of a pattern. And that pattern would be that, say I plot all the distributions and I do that and I draw a mapping of it, I'd see that there'd be a slight rise or concentration towards a particular value or a particular range in the middle. And this concentration is what will later give us the average of the entire sample set, and I'll show you how. So say we take a sample set of larger size of say 200. So now the sample set of size 200, and plot the same distribution of all the averages we find in it, and we'd see that this graph, this concentration just starts becoming more and more towards one single particular value. So if we take uh, the averages of sample sets that have an infinite number of members in them. Yeah, so an infinite number of heights. Now, this need not always be infinite, it could just be sufficiently large. But for the sake of convenience, we're going to take an infinite number. And if you find the averages of all such sets, we could see, or we would be able to see, that all of them would tend to one single value. That is one single value. All the averages would be the same, and this value is indeed the average of all human heights on Earth. And that is the beauty of central limit theorem. It states that even if you have a sufficiently large sample size, which we did, we had a sample size of 7 billion people, that was sufficiently large enough, and allowed us to take sample sizes of very big sizes. And it also had a finite level of variance. And if we mapped all of these and we plotted the distribution, we'd be able to reach a single answer, a single average, which would indeed be the average of the entire sample set. And that is the central limit theorem. Now we'll start the application part of our project. And for this, we have chosen a very interesting topic, which involves central limit theorem and how it affects the societal behavior of animals, in specific bees in this case. Now, as a recap to central limit theorem is a statistical principle that states that as the number of repeated samples from any population increases, the variance among the means of the samples will decrease, and means will become more normally distributed, or we'll get closer to a normal value for average of all the data that we have been provided with. Now, the research paper has been written by Mark 1 Stevens, Kartha Hogendoon, and Michael P. Schwartz. It states that it has been conjunctured that central limit theorem has a potential to provide benefits for group living in some animals via greater predictability in food acquisition if the number of foraging bouts increases with group size. Now, in context of bees, this states that as the number of foraging bouts increases. Now, foraging bouts is just another way of saying the number of trips to collect food increases, the variance of brood weight, which is again a very fancy way of saying amount of food collected per trip, will decrease. And this is in alignment with CLT, which states that as a number of repeated samples, in this case the foraging bouts, increase, the variance among the sample means, in this case the variance of brood weight, decreases. Now, if I was to put this in a better context, I could explain the same by drawing a graph. Now, keep in mind that this is not the graph that is provided in the research paper, but instead a very generic graph associated with CLT, which will help in better understanding and not make things too complicated. So, say I take sets of foraging bouts, or of brood weights per foraging bouts. So, say I take sets of 4 of amount of food collected per foraging bouts, and I find the average. Now, if I was to plot this data, distribution graph, I would find that it would look something like this. Now, as you can see, a rise in this section, this is a rise towards a normalized value that would, if ever obtained, provide us the average of the entire sample set. So let's increase the size of the sample set over here. Let's consider, as we did when explaining CLT, sets of very large size, tending to infinity but not quite infinity, very large size. If we were to use such sets and a large number of such sets, we'd find that the average brood weight or the average amount of food collected per trip would almost reach a normalized value. This normalized value is indeed the average or very close to the average of amount of food collected per trip. Now, what's interesting and what has been noted by the three researchers is that as the population of the community, as the population of the bee community increases, this average, this average value, this value in fact increases. So as the population increases, the number of foraging bouts increases, and as well as that, the amount of food collected also increases. Now, why is this topic so interesting? This topic is especially interesting because it brings in light the direct correlation of societal behavior. So, societal behavior of animals in general, not just bees, animals including us humans. Societal behavior that we've been following for millennia, and a direct association of this with statistics. So, the very concept that statistics can be used to predict societal behavior is something that seems to be of great interest, especially to us, and that is why we have chosen this topic. That was a presentation for application. Thank you.